Hello everyone, this is Digbijoy Nath from Center for Nanoscience and Engineering at Indian Institute of Science, Bangalore. Welcome to this course on basics of semiconductor microwave devices, and today will be our first lecture. So today is an introduction lecture, and actually the first couple of lectures are about introducing the course, about understanding the various aspects of microwave device applications, microwave electronics, and also we will walk you through a historical overview or historical perspective of this development of this field. Okay. So in this course we shall be using a combination of slides and whiteboard, predominantly whiteboard, but also we will be using slides, and those will be uploaded as and when they are the slides are used. But today and for today and the next lecture we shall be not using slides, we shall use the whiteboard predominantly. Okay. So we will switch to whiteboard now. So this course about basic semiconductor microwave devices, it's a 30-hour lecture and 30-hour course, and we will have basically 60 lectures of 30 minutes each. Okay. So basically we have a few around 10 to 12 weeks I believe, and I will just quickly go through the outline so that you know what we are going to talk about. So in the first week, okay, week number 1, we will have 4 lectures of half an hour each, and we will basically talk about introducing the course, and historical perspective of how this field has evolved, and the applications of RF devices and RF systems, because they are everywhere, we depend on them every day. So we will talk about their application, the systems, historical overview. Week 2 we will have around 6 lectures, and we shall basically recap the heterojunction. Okay. We shall recap the heterojunction physics and heterojunction devices. Why? Because a lot of microwave devices are actually are made of heterojunction or compound semiconductor devices. We shall also introduce gallium nitride and its alloys, because gallium nitride is a very emerging and critical wide bandgap technology for high power high speed amplifier design. Okay. And then we will have a brief overview of things like Schottky multipliers, okay, and varactors, okay, and varactors, which are also useful RF devices. Week 3 we will have around 4 lectures, and we will basically talk about transferred electron devices such as gun diodes. These are diodes, these are 2 terminal diodes, and we will also talk about IMPAT, which is basically an avalanche transit devices. We will of course give you a feel in reality where these devices are used or likely to be used, why are we using those devices, in what aspect of RF actually we need those devices. We shall talk about that. For instance, you can make using IMPAT diode, you can actually generate RF signal of certain power, so it is used for RF generation for instance. Okay. Things like that, we will definitely talk about that. Week 4 has about 6 lectures, and this is about compound semiconductor, traditional compound semiconductor, and this is a very important part of the course. We shall talk about 3-5 MESFET, okay, compounds gallium arsenide system, indium phosphide gallium arsenide system. We will talk about 3-5 MESFET, we will talk about their physics, we will talk about their carrier transport, okay, and we will talk about their IV characteristics, we will talk about the load line for instance, then we will talk about transconductance GM, we will talk about some amount of fabrication also of these compound semiconductor devices, and we will introduce the Johnson figure of merit, okay, which is a very important figure of merit for RF devices. Alright, I will go to the next page. So that was week 4, and then week 5, okay. Week 5 has 4 lectures, and here we will continue with the 3-5 HEMT, okay, 3-5 HEMT. We will essentially introduce the concept of modulation doping, so MODFET and HEMT, and then we will understand the physics of modulation doping, okay, and how the 2DG is formed. We shall talk about breakdown of such devices, alright. We shall talk about gain, we shall talk about traps, okay, and we shall talk about dispersion. These things may not be very clear right now, but as we discuss it will become clear, okay. Then week 6 we will again have 4 lectures. Here we will introduce something called pHEMT or pseudomorphic HEMT, which is a very important RF device actually. We will also introduce advanced concepts in HEMT such as recess gate, okay. We will introduce field plate, okay, and also we will talk about multi-finger devices, because that is how you get higher power, multi-finger HEMTs, okay. We will talk about things like power cell for combining many of these multi-finger devices. Then we come to week 7, okay. Week 7 we will have 6 lectures, and here we will talk about gallium nitride HEMTs. Why do we use wide bandgap semiconductors for RF? Okay. We will also understand effects of say substrate issues such as substrate and process related issues for GaN HEMT. We will talk about the concept of virtual gate, okay, and current collapse, which is an extremely critical phenomena in gallium nitride HEMT, current collapse. We shall talk about how to design the stack of GaN HEMT for RF, okay, for RF how do you design the stack HEMT. We will talk about compensation doping in that when you talk about the stack HEMT, okay, and we will talk about multi-finger again just like we talked in the gallium arsenide case, multi-finger, and we will talk about some of the practical aspects of this. You know, we can show pictures for instance of commercially available gallium nitride or gallium arsenide devices, bare dies, matched dies, amplifiers, and we will walk you through that, okay. That was about week 7. Now I will come to the next page, week 8, okay. In week 8 we shall have 6 lectures again, and here we will introduce RF CMOS. CMOS after all is the most widely used technology today in general, but for RF electronics CMOS has a very particular application in this low power, low voltage kind of all the dominant electronics that we see around us which are low power, low voltage, you know, scalable, they are all CMOS actually, okay. So we will introduce the basics of CMOS RF, and then we will switch to LDMOS. LDMOS is basically the cousin of CMOS, but it is for high voltage, high power. So it is a basically MOSFET, but it is a high voltage high power MOSFET, and we will understand from LDMOS how it is useful for RF applications such as we will understand the device physics we will talk about and transport of course, okay. Then we will talk about the breakdown of such LDMOS which is very important. We will talk about on resistance, okay. We will talk about something called snapback in LDMOS. Then we will talk about the layout and design of such RF LDMOS, okay, and then we will discuss things like bond pad manifold. By the way, these bond pad manifolds are also important for HEMTs and gallium nitride HEMTs and other things, but we here will talk about in more details, and then we will talk about the concept called resurf, reduced surface electric field, and we will see what resurf means. It is a very important concept for LDMOS, okay. So this will be week 8. Then we have week 9. In week 9 we will have 4 lectures, and here we will introduce bipolar devices or BJTs. So we will talk about bipolar for RF, bipolar devices for RF, and how does HBT works. What are things like for instance Early effect or Kirk effect, okay. Maybe you already know these things, but we will have to recap them in the context of RF. What is about gain, what is about common emitter and common base operation of HBT for RF application, you know, and then what is a small signal model of such you know BJT, RF BJT. Then we will come to week 10. Week 10 has also 4 lectures, and here we will talk about more advanced concept of RF bipolar devices such that we will talk about base design, how we design the base for RF HBT. We will talk about collector design, okay. We will talk about collector design. We will talk about things like emitter ballast. We do not know right now what it is, but we will definitely know, okay, what is emitter ballast. We will also introduce silicon germanium bipolar devices, okay, silicon germanium bipolar devices, and we will definitely also in this week talk about HBT versus FET for RF or microwave, not for CMOS, and also not for logic or processing or you know things like low power memory, but we are talking about RF electronics, what are the differences between FET and bipolar, and then we will finally conclude with a fabrication of HBTs, okay, that is in week number 10, okay. And then finally in there are 2 more weeks, week 11 and then week 12, okay, and that will conclude our course. So week 11 we will have 6 lectures, week 12 also will have 6 lectures. So here we will basically, because these are the last 2 weeks, so in week 11 and week 12, so here we will introduce some of the basics of microwave engineering concepts, okay. We will introduce concepts of microwave engineering such that we talk about S parameters, okay. We talk about 2 port Z parameters, network analysis for instance. We will talk about the concept of impedance. We will also introduce Smith chart, okay, very briefly, and we will talk about concept of impedance matching. Z matching is impedance matching, okay. We will talk about de-embedding the parasitics, okay, de-embedding the parasitics, and we will also give a very brief introduction of transmission lines, waveguides, you know, things like for instance coplanar waveguides, you know, that are used on FET, okay, BJT. Again, all these things will be from the point of view of devices. I mean, we will introduce them as it is, but we will try to not forget that we are a devices course. So, we will approach them from the device side, not from so much from the system side. Okay. The last week, week 12, we will derive the cutoff frequencies, for instance FT, Fmax, okay, cutoff frequencies of FETs. Okay. We will talk about maximum available gain, maximum signal gain, we will talk about power added efficiency, we will talk about gain in general. Okay. We will talk about linearity and linearity from a device point of view, what is meant by linearity from a device point of view and what is it meant from amplifier point of view. Okay. One sec. And then we will talk about basics of power amplifier design, I mean basics of power amplifier I would say, and classes of operation, different classes of operation, class A, class B, what are those classes. Okay. And lastly we will just try to touch upon on basics of RF packaging, okay, and thermal management. Okay. Just a brief overview. Okay. So, this is basically in a nutshell the outline of this course. So, we will go through again. So, in first few lectures will be introduction, historical overview, then we recap heterojunction, we go through gallium nitride basics and Schottky multiplier varactors in general, then we talk about transfer electron devices like gun diode and impact diode which is an avalanche device, then we talk about 3,5 gallium arsenide based MESFET in details, then we talk about gallium nitride based HEMTs. Okay, before that we will talk about just general HEMTs of gallium arsenide and pseudomorphic HEMTs, including concepts such as recess gate, field plate, etc. Then we go to gallium nitride HEMTs, similarly virtual gate, current collapse, fabrication, multifinger, etc. Then we come to RF CMOS and focus primarily on LDMOS for high power high voltage RF application, and then we go to bipolar devices 2 weeks, BJTs, HBTs, and how basically things like emitter ballast and collector design are useful. Now lastly, in the last 2 weeks we will introduce basics of microwave concepts such as S parameter, Smith chart, impedance matching, transmission line, coplanar waveguides, and also about classes of amplifier, power amplifier, maximum gain, linearity, mostly trying to understand from the device point of view, and of course packaging and thermal management. Okay. So, this is the outline of this course. Okay. This is the outline of this course, and as you may see that this course builds up on the basics of semiconductor devices that you may have learned in other courses. So, you need to have that background on semiconductor to appreciate this course. Okay. Now RF course, of course RF circuit design or microwave engineering courses are there are many excellent such courses. So, this course is not about that. Okay. But even then we need to understand about RF microwave. Okay. Because we are going to talk about devices, we need to understand what RF microwave frequencies we are talking about. So, these are a part of electromagnetic waves, all of you know that, right. Electromagnetic waves that can propagate in free space, that can also go through any media. The idea is that whenever you have this electromagnetic waves in a certain frequency range, okay, we will come to the frequency range very soon. The idea of having this RF circuit is that you bring them on a semiconductor substrate. Okay. So, this is suppose your semiconductor substrate and you have a source, a drain and a gate, for instance. You want to bring this signal coupled to the substrate and bring it to the device, okay, and do some processing, amplifier, etc., etc. Similarly, you have to send this signal out also. Okay. They send this signal out, transmit towards, for instance in cell phone communication, in the nearest tower you have to send it there, and you have to receive the signal from the nearest tower, for instance in a cell phone communication. But there are vast applications of RF electronics in general and hence RF devices, and there is a wide range of frequencies that are used, but we will not talk about everything. We will only confine ourselves to what are predominantly used in common microwave applications. So, electromagnetic waves can span a lot, it can go from terahertz, optical, X-ray, gamma ray to microwave, okay, radio waves. When we talk about RF and microwave, so RF essentially historically these are frequencies that are used in radio communication, and so all this VHF, LF, low frequency, high frequency, very high frequency, etc., etc. People started from hundreds of kilohertz up to hundreds of megahertz. So, typically RF frequencies span from a few hundred, a few tens of megahertz to few hundreds of megahertz, and it can go all the way to gigahertz. Okay. But when it approaches gigahertz we call it microwave. Okay. So, RF and microwave are used interchangeably, but microwave is a kind of slight, it is under the RF umbrella. Okay, it is under the RF umbrella, but microwave is typically we talk about say 1 to 30 gigahertz, okay, or 3 to 30 gigahertz is where we call it microwave. If it is say hundreds of megahertz, we can still call it RF, but we don't call it as much microwave. Okay, and above 30 gigahertz we call it millimeter wave, because the wavelength of the signal approaches a millimeter. So we call it millimeter wave. From 300 to 30 to 300 gigahertz we call it millimeter wave, and beyond 300 gigahertz we call it sub-terahertz, then we come terahertz, etc., etc. Okay. Now there is enormous a number of applications, especially the applications had exploded after the World War II, when microwave engineering and application of RF signal became very important for strategic sector, for even civilian uses. But right now we are seeing an explosion. Why? Because all data is communicated wirelessly. Most of the data is communicated wirelessly, I would say, because of personal gadgets, handheld mobile gadgets. You carry your even laptop around, you have a cell phone, iPad, now smart watches, smart glasses. So this data has to be transmitted from one point to another point wirelessly in most of the cases. Okay, you are going to transmit data wirelessly, and whenever there is a wireless transmission of data, your cell phone, your iPad, your smartwatch, you need to send signal, transmit, you need to receive signal. Okay, and these are electromagnetic microwave signals predominantly that you have to send and receive, and on your chip, on the semiconductor wafer, you need to process this signal. Okay, so there is a bunch of microwave devices and components like oscillators, mixers, synthesizers, filters. They are all built into the substrate, the semiconductor substrate, so as to work with these microwave devices. Okay, or these microwave signals that are coming in. So data communication is booming, and by data communication we predominantly mean wireless data communication, say 5G, 6G, etc., even otherwise. Okay, Wi-Fi. So because of this huge boom, RF and microwave electronics are seeing an unprecedented expansion in application. The system designers have a more and more stringent requirement now. For instance, when you have so many applications running in a cell phone, your battery will be drained very fast, because the RF power amplifier, for instance, it guzzles up the battery very fast. So the designer or the circuit designer, we has to place extreme stringent constraint. Okay, the device has to have certain linearity, efficiency, power, gain, etc., etc., so that it gives all the functionalities you need without compromising or without draining the battery too much. So the RF device engineer is in a very tight spot, because he or she has to cater to an increasing demand on things like efficiency, PA's efficiency, gain, power, linearity, and also size of the die. You need miniaturized dies, lightweight miniaturized dies, thermally managed dies, but they should give you outstanding efficiency, gain, power, linearity. It becomes a very difficult task, because the system designer wants all of this. Only then your next iPhone, or whatever new phone is coming out, can incorporate all of these functionalities without draining the battery very quickly. Okay, so this is one very big application of RF electronics today, microwave electronics today. The other main or very important application is radar and satellite communication, SATCOM. These are strategic applications, which means these are military and space sensitive. So these have to be indigenously developed. There are import restrictions on such technologies. Radar is needed for essentially radio imaging and radio detection and ranging. You need to send microwave signal of high power to basically detect an enemy aircraft or enemy missile. So radar is of different, they operate at different frequencies, different power levels. Similarly, satellite communication, all this PSLV, Astrosat, Chandrayaan, Aditya mission, all of this of course needs satellite communication. They talk to each other, they also talk to the ground. For instance, in the recent Chandrayaan mission, you had the Pragyan and the Vikram, right? They have to communicate with each other. That frequency of operation or communication could be different from the frequency at which the lander or the rover is actually communicating to the earth. Okay, so the frequencies could be different. There are different frequency bands that are used for this communication. So those satellite communication, they use something called transponder, transmitter and a responder, and slightly different from a transceiver, by the way, which is a transmitter and receiver that is used in a cellular infrastructure. So they all use microwave devices for transmitting and receiving. The antenna is used of course, but to process the signal, to amplify the signal, you need these microwave devices in a microwave circuit. Okay, so these are some of the very broad application and very important applications of microwave electronics. But other than that, there are abundant applications of microwave electronics. Okay, you have remote sensing. Okay, you have maritime communication, you have radio astronomy. Okay. In general, non-critical satellite communication also could be there. There is all kind of RFID that you use to switch on your car door, vehicle door for instance. There is telemetry, there is oceanographic radar, there is anti-collision radar of vehicles, correct. Then there is communication link, weather, with climate weather control or weather monitoring, not control, monitoring radars that are there. So any kind of wireless data transmission or detection, receiving, all these things are dependent on RF electronics. So we need RF devices for all of this. So that being said, there are many frequency bands that are used. Okay, there are many frequency bands that are used. So we will typically classify them in the nomenclature that RF microwave electronics community uses them. So we have L band, S band, C, X, Q band, K band, and which also means sometimes Ka band. Then you have Q band, V band and W band typically. These are different frequency bands or ranges in which different applications are being targeted. So for instance, L band is typically and there is sometimes overlap. People say it is 1 to 2 gigahertz, but some people may say it is up to 1 gigahertz also. Okay. Similarly, S band is 2 to 4 gigahertz. Okay, 2 to 4 gigahertz. C band is 4 to 8 gigahertz. X band is 8 to 12 gigahertz. Q band is 12 to 18. K-Ka band is 18 to around 30. Okay, that is Ku-Ka band. And then Q band is from 30 to 50. V band is 50 to 75 and W band is 75 to around 100 or 110, okay, gigahertz. These are different frequency bands across which different applications are being used. Okay. For instance, in L band you have a lot of military radars, especially maritime radars, and actually you also have most of your cell phone, by the way. All your cell phone operations are around that frequencies right now. However, they are moving to 5G communication, and 5G will, the frequency of 5G operation will depend on the country. US, Europe, Australia, Japan, India could have different frequencies for 5Gs. For in India, 5G usually refers to sub 6 gigahertz, which means we are talking about less than 6 gigahertz. So one of the common frequency bands is N78, which is for instance 3.7 or 3.8 gigahertz. Okay. So those are the 5G, people are deciding on those 5G frequencies, for instance for cell phone. S band, okay, then if 5G comes in here 3.7, 3.8 gigahertz, then S band is used in that. Okay. But S band is also useful for satellite uplink, downlink, oceanic radars, etc. C band is heavily used by, for instance, ISRO, okay, for remote sensing, for satellite communication, satellite radars, weather radars, downlink, satellite downlink. They are used extensively by ISRO and such, they have a very high interest in C band radar, C band satcom, satellite communication, remote sensing, and even military also uses C band radars. For instance, X band is also primarily used by military for radar. Okay, for military radars you need X band, this thing. Q band, Ka band, they are a little high frequency, they are also useful for radars at different frequency bands. Okay, they are useful for different frequency band radars. They are for when we go to Q and V band, for instance, you have anti-collision radars. Okay, 77 gigahertz is anti-collision radar in the vehicle. Weather radars are used, airborne radars, for instance, missile radars, seekers. It could have different applications in all of these different bands. Okay, so again in W band is typically useful for missile, missile radars, for instance. So they are chosen based on the absorption of these different wavelengths in the atmosphere, in water vapor. They are also used in keeping in view what enemies might be using, how difficult it is to jam them, how how sensitive, how well you can have this, how well you can actually ensure that they are not jammed or detected by enemies, for instance. So many of these considerations come into picture, and so military radars use a lot of these frequencies, but typical cellular communication is here. Okay, and of course in some countries 5G communication could also happen in Ku or Ka band. 26 to 28 gigahertz is also being widely speculated, or not speculated, it is coming up to be used in 5G communication in different countries like North America, Canada, etc. Okay, so that those frequencies are used. So these are in a general outline of different frequencies that are used for microwave electronics. Now whenever there is a microwave, there is microwave engineer. Okay, there is microwave engineering which talks about different components of microwave systems, for instance resonators, okay, resonators, circulators, okay, circulators, couplers, okay, power dividers, power splitters or power dividers. Of course everything is built on transmission lines, not everything, but transmission lines are very important, and then you have this different kind of waveguides, of course, okay, and then these are different kinds of microwave components, filters for instance, okay, and then of course amplifiers, low noise amplifiers, power amplifiers, oscillators. Oscillators are useful for generating RF signal. Amplifiers amplify the signal. Filters can selectively select some wavelengths, okay. Power splitter can split up the power on power combiners also there, by the way, they can combine power, okay. Similarly there are couplers. Then circulators are 3-port network RF devices. There are resonators, they will have their own resonating frequencies around which we can build some of these important RF concepts, okay, the devices and systems. So all of these are actually microwave engineering, and people come up with more advanced and more improved designs of different components here, filter design, amplifier design, oscillator, etc. Then there is this RF circuit design, okay, RF circuit design, and typically when you talk about CMOS silicon or BiCMOS is basically bipolar CMOS together. We talk about low power, low voltage RF circuit design, which is by the way very widely used. So RF low power low voltage RF design, which depends on CMOS, BiCMOS, they are the RF IC designers, okay. You are talking about CMOS RF IC, and we talk about many kinds of things there, right, from noise to PLL, phase lock loops, even amplifiers, low power amplifiers, low noise amplifiers, how to design, okay. And then we come to the designing, for instance in a cell phone we can have a front end. The entire front end of a cell phone could have this transmitting chain, this receiving chain, we call them the transceiver chain. So people design the transceiver chain, okay. Then there are dedicated PA designers. PA stands for power amplifier. Power amplifier is actually the most power hungry block on your cell phone. So PA designer is a separate category in itself, and PA designers actually work with power amplifiers, and they design power amplifiers based on the requirements, and they are very advanced power amplifier designs such as Doherty design, and they have different categories and classes of operation like class F inverse, J inverse. It's fairly complicated area, but power amplifier is one of the most critical design components in a cell phone, for instance. You need it also for radar, okay, don't get me wrong, but it's a very critical aspect of the cell phone. So power amplifier designers are there. Then we have also MMIC designers. MMIC stands for microwave monolithic integrated circuit, and MMIC basically is you implement the entire functionality on a single chip, on a single die, you fabricate everything. You don't bring different or discrete components and put them on the same chip, you actually combine everything out there, okay. So this is called microwave monolithic integrated circuit, and microwave monolithic integrated circuit designers, MMIC designers, could make, for instance an amplifier using a MMIC. They can make a low noise amplifier, they can make a mixer using MMIC. Sometimes even the entire receiver transmitter chain could be also built in an MMIC, okay. So MMIC designers are also different because many applications do not necessarily require MMIC, but some applications do preferably require MMIC, okay. The idea of this course is actually to understand the devices that go into all of these different applications, okay, most of these different applications, okay. So the HEMTs, the FETs, the varactor, the gun diode, and all the LDMOS that we are going to talk about, the HBTs, we will try to understand the devices that actually go into most of this. Some of these may not need a device, okay. For instance, just a transmission line or a waveguide is not a device per se, okay, but many of these applications need devices. So we are going to talk about the devices, okay, and we will not talk as much on CMOS. We have some coverage on CMOS RF device per se, but not so much, very likely, because the CMOS RF actually of course there are many more advanced versions coming up, but in general it's just a MOSFET and you have to take care of the parasitics, okay. And CMOS RF lags behind the digital 7 nanometer 5 nanometer node by about around maybe 10 to 15 years, okay. It lags behind that, and CMOS RF we quickly talk, it has more to do with the RF circuit design in that case, rather than discussing too much about the CMOS RF CMOS. We will discuss CMOS RF, the basics of it, but in general it is just like a MOSFET in a way, okay, with some parameters, with some conditions that you have to keep in mind for RF operation. Okay. So, we will not spend as much time on RF, we will predominantly spend time on compound semiconductors. We will also talk about LDMOS, silicon LDMOS devices for RF power. Okay. So, with that I think we will conclude today's lecture on the first part of introduction. We have more parts coming up. Okay. So, today we will conclude our lecture 1 on the first part of the introduction of RF systems, RF devices, and what this course is all about, what this the outline of this course and the applications of various frequency bands, what are the importances, and what this course is actually going to seek, what this course is going to understand, we try to understand in this course. So, with that we will conclude today's lecture, and thank you everyone, and we shall basically see you in the next lecture, which will be lecture 2, and we will continue from where we left here today. Thank you.